The Norwegian Sea in January does not permit neutrality. At 71 degrees north latitude, the ocean becomes a participant in everything that happens on it. The air temperature at the surface is -23 degrees Celsius. The water is 2 degrees above freezing, and the wind comes off the ice shelf to the northeast at 34 knots, driving a spindrift of frozen salt crystals horizontally across any exposed surface. USS Donald Cook makes 17 knots into the weather, her bow rising on each swell and crashing back with a shudder that can be felt in every frame. Ice has been forming on her superstructure for 6 hours. A slow accumulation on the radar masts, the railings, the external ladders, the CIWS barrel housing, anywhere the wind-driven moisture contacts a metal surface that is already at the ambient temperature. The ice is not dramatic. It is persistent. Every 2 hours, the deck crew goes out to chip it, working in pairs with mallets and safety harnesses in conditions that make the task feel less like maintenance and more like an argument with the climate. It is 1:47 a.m. The ship is operating as part of a NATO patrol element, conducting freedom of navigation operations in the eastern Norwegian Sea, 312 nautical miles north-northeast of Tromsø. The nearest friendly vessel is a Norwegian frigate, 47 miles to the southwest, running her own patrol line. The nearest unfriendly thing is a Russian coastal radar installation on the Kola Peninsula, 280 nautical miles to the east, which has been tracking the Cook's position continuously since she crossed the 70-degree parallel 14 hours ago. The tracking is not aggressive. It is methodical. The Kola radar network exists for exactly this purpose: to know where NATO's surface combatants are at all times in the waters adjacent to the Northern Fleet's operating area. The Cook's electronic warfare suite has been logging the Kola radar's emissions throughout the transit. The EW operator has noted 3 changes in the radar's operating frequency in the past 4 hours. Normal cycling, consistent with routine surveillance. At 1:43 a.m., he notes a 4th frequency change, and then a 5th in rapid succession, and then a shift to a mode he has seen before in training intercepts, but has not previously seen in actual operations in this theater. He classifies it. He stares at the classification for 4 seconds. He picks up the sound-powered phone to CIC. CICEW. I have a weapons-grade targeting radar active, bearing 095, consistent with a Bastion coastal defense battery. Repeat, weapons-grade targeting. The officer of the deck orders general quarters at 1:44 a.m. The general alarm sounds. 281 sailors move to their stations in darkness and cold. The passageways briefly filling with the sound of boots on steel and the mechanical click of battle lantern handles being freed from their brackets. In CIC, the watch team shifts to a wartime posture. Tracking contacts are elevated to active engagement status. The MK-41 VLS operator confirms cell status. The SPY-1D is already at full active scan. At 1:46 a.m., the Bastion battery launches. From the battery's perspective, it is a single salvo, 1 P-800 Onyx missile and 1 Zircon hypersonic. The Onyx is the primary engagement system. The Zircon is the follow-on. Standard doctrine for a high-value surface target. The Cook's Aegis system detects both launches 16 seconds after ignition. Track files open automatically. The SPY-1D classifies the slower contact immediately. P-800 Onyx, supersonic. Track confidence high, intercept solution generated. The second contact is different. The radar return is small, the velocity is extreme, and the flight profile is not one the fire control computer's track library has processed in a live engagement. The operator overrides the auto-classification and designates it manually. SM-6 is assigned to the Onyx. The Zircon track is held for SM-6 engagement if a second missile is available after the first intercept. The SM-6 intercepts the Onyx at 22 miles. The debris falls into the Norwegian Sea in 3 pieces. The Zircon is traveling at Mach 8.2. Its flight profile is a shallow descent from high altitude, not sea skimming, but a terminal phase acquisition geometry that limits the radar's engagement window to the final 18 seconds of the missile's run. The second SM-6 leaves the VLS cell at 1:46:58 a.m. The Zircon's terminal velocity is approximately 2,750 meters per second. The SM-6 intercept is not a clean intercept. The proximity-fused warhead detonates within lethal radius of the Zircon. But the hypersonic vehicle's kinetic energy carries the fragmenting airframe forward through the detonation envelope. The Zircon does not reach the cook. It passes 34 meters above the flight deck. Traveling Mach 6 at that point, its fragmented airframe shedding burning propellant and high-velocity debris across a 200-meter path that ends in the ocean 180 meters beyond the ship's stern, 34 meters of vertical clearance. The shockwave reaches the cook in the same moment as the debris field. A wall of compressed air moving at the speed of sound that strikes the ship from above and starboard simultaneously. It is not a gentle pressure increase. It is an instantaneous transition from ambient pressure to approximately 4 atmospheres overpressure across the entire exposed surface of the ship, lasting 0.12 seconds. Every external-facing antenna, radar face, and sensor array on the top side receives this loading simultaneously. The SPY-1D phased array faces 4 panels, each approximately 3.7 meters by 3.7 meters, are designed to survive significant pressure loading. But their design envelope was written for horizontal threats, not a shockwave arriving from 34 meters above at hypersonic airspeed. Array face alpha takes the worst of it. The phased array panel deflects inward by 11 millimeters at the panel center. This deformation is not catastrophic. The panel does not crack. The waveguide connections do not sever. But the deformation shifts the phase relationship of approximately 340 of the 4,480 radiating elements across the face. And the SPY-1D's built-in test system detects the misalignment as a calibration error. The radar's protective software responds as designed. It takes face alpha offline and redistributes the surveillance load to the remaining 3 faces. This is an automatic action, completed in 0.3 seconds. The crew does not have to do anything. The ship loses 25% of its radar coverage on the threat axis, the bearing from which the Bastion battery fired. This is the design degraded mode response. This is not the problem. The problem is the seawater cooling system. The SPY-1D radar generates enormous heat. The phased array transmitter modules operate at high power density, and the heat they produce is removed by a seawater cooling system that circulates chilled seawater through heat exchangers embedded behind each array face. The cooling system for Face Alpha and Face Bravo shares a primary heat exchanger mounted in the forward equipment room, 1 deck below the bridge. The seawater supply for this exchanger enters through a hull penetration fitting on the starboard side, runs through a 3-inch supply line to the exchanger inlet, and returns through a parallel line to the overboard discharge. The supply line runs a short section through a bracket weld assembly where it passes through the hull's structural frame at frame 19. The shock wave from the Zircon's passage transmitted a pressure pulse into the ship's structure through the topside panel deflection. The pulse traveled down through the superstructure, framing into the hull frames at the acoustic velocity of steel, approximately 5,100 meters per second. At frame 19, the bracket weld assembly on the SPY-1D cooling water supply line was subjected to a transient loading that lasted 0.0006 seconds and had a peak force approximately 1.4 times the assembly's fatigue design limit. The weld did not fail immediately. It developed a hairline crack along the heat-affected zone. The cooling water supply line continued operating normally for the next 4 minutes and 11 seconds. Then the crack propagated to the pipe wall. The leak began as a seep, a few drops per minute along the weld line. Within 6 minutes, as the pipe's operating pressure cycled with the cooling demand of the radar transmitter modules, The crack extended to 17 millimeters. The flow through the crack became a stream. The stream began depositing water on the forward equipment room deck. The forward equipment room deck sits directly above the ship's forward main electrical distribution panel. At 2:04 a.m., the water reached the deck drain, which was partially blocked by a rubber mat placed over it during icing operations to prevent the drain from freezing. The water pooled. At 2:06 a.m., the water found the cable penetration into the electrical panel below through a conduit seal rated waterproof, but not designed for standing water on its top surface. The seep through the conduit seal was slow. It was also continuous. At 2:09 a.m., the EW operator picks up the sound-powered phone again. CIC-EW. I'm losing receiver sensitivity on the 090 to 180 arc. Looks like an equipment issue, not a jamming profile. The combat systems officer is in CIC. He pulls up the SPY-1D system status display and sees exactly what the EW operator is seeing. Face Alpha offline on the automatic degrade, as expected following the shockwave. Face Bravo showing degraded receiver performance. Sensitivity dropping at a rate consistent with a cooling issue. If Face Bravo's transmitter modules overheat and the system takes the face offline automatically, the ship loses coverage on the entire eastern arc. The Kola radar is to the east. The Bastion battery is to the east. The eastern arc is exactly where the ship needs to be looking. He calls the chief engineer. The chief engineer is already in the forward equipment room by the time the call reaches him. He has been doing his own post-event walkthrough since the shockwave hit, checking for damage the automated systems might not have captured. He finds the pooled water on the deck at 2:11 a.m. The pool is 7 inches across. It is actively draining through the conduit seal. He traces the source to the bracket weld crack on the cooling line in 30 seconds. The crack is visible to the naked eye as a dark line along a lighter weld bead, with a mineral deposit pattern consistent with a seep running for several minutes. The cooling line is pressurized at 45 pounds per square inch. The crack is running along a weld seam approximately 3 inches above a structural frame. Access to the fitting is tight. The line runs through a bracket assembly that leaves approximately 4 inches of clearance on each side. Not enough for a standard C-clamp repair approach. The fitting itself cannot be isolated without shutting down the entire SPY-1D cooling supply, which will cause the radar to begin thermal shutdown within 8 minutes. The chief engineer looks at the crack, looks at the clearance, looks at the drain flowing into the electrical panel below. 2 problems. One is getting worse. The other is already worse. He calls DC Central. DC Central, Engineering. I have a cooling line crack in the forward equipment room. Frame 19, SPY-1D supply circuit. I also have water ingress into the forward electrical distribution panel through the frame 19 conduit. I need the forward panel isolated immediately, and I need 2 people with repair materials at frame 19 in 4 minutes. The chief engineer goes to the forward electrical panel himself, because the panel isolation requires a specific procedure, and he is not willing to talk someone through it by phone while standing next to the panel himself. The panel is in the space below, accessible through a scuttle in the equipment room deck. He drops through and inspects the top of the panel housing. The conduit seal is weeping. He can see the moisture on the panel's top surface. The panel is not yet faulted. The water has not reached the bus bars, but the rate of ingress means it will reach them within an estimated 12 to 15 minutes if the source is not isolated. He cannot isolate the source without shutting down the cooling supply. Shutting down the cooling supply will take SPY-1D Face Bravo offline within 8 minutes from thermal buildup. Without Face Alpha and Face Bravo, the ship's radar coverage on the eastern arc drops to 0. He cannot let the water continue. He cannot take the radar down. He is choosing between 2 necessary things that are mutually exclusive within the current system architecture. He is in the panel space for 40 seconds, thinking. Then he climbs back through the scuttle. The forward equipment room has a damage control locker on the aft bulkhead. He opens it. Standard contents: wooden plugs, speed patches, C-clamps, SCBA equipment, fire boundary materials, and, on the second shelf, in a yellow case that has not been opened since the pre-deployment DC locker inspection, a tube of two-part marine epoxy rated for use on pressurized systems up to 150 psi. The tube is marked for pipe repair applications. The label says, "Do not apply to actively flowing leaks. Surface must be dry." The surface is not dry. The leak is actively flowing. The chief engineer reads the label. He reads it again. He sets it down and picks up the sound-powered phone to DC Central. DC Central, does anyone on watch have experience with pressure seal epoxy application on wet surfaces? The response comes back in 20 seconds. The senior hull technician, currently posted at Repair Party 3 on the aft deck, has done exactly this. A wet surface epoxy application on a pressurized seawater line during a shipyard availability period where the line could not be dewatered. Not standard procedure. A field expedient. He knows how it was done. Get him to frame 19. Now. The hull technician arrives at 2:17 a.m. He looks at the crack. He looks at the clearance. He asks for the epoxy, a rag, and the heat gun from the DC locker. The heat gun is in the DC locker. It runs on 110 volts. The forward equipment room has one 110-volt outlet on the port bulkhead, live on emergency power. He explains the technique as he prepares. The key to epoxy adhesion on a wet pressurized surface is not drying the surface. That is impossible with an active leak. The key is displacing the water from the application zone for the minimum time required for the epoxy to achieve initial set, which at the current air temperature of -2 degrees Celsius in the space. The forward equipment room is cold because the ship's heating system is fighting an Arctic exterior temperature that winds continuously. Will take longer than the manufacturer's nominal 2-minute set time, probably 4 to 5 minutes at this temperature. The water needs to be displaced from the weld crack area for 4 to 5 minutes while the epoxy cures under pressure. He uses the heat gun on the crack area for 90 seconds, displacing the surface moisture and slightly warming the steel. Not dry. Warm enough. He mixes the epoxy in a ratio by weight that he estimates from experience rather than measuring. Heavier on the hardener in cold conditions. He applies it directly to the wet weld seam with a putty knife, forcing it into the crack under manual pressure, working from one end of the crack to the other in a single continuous motion. He applies a second layer immediately over the first, building a ridge approximately 5 millimeters thick along the full length of the crack. Then he presses his thumb against the epoxy bead and holds it there. This is the technique. Direct manual pressure on the uncured epoxy, sealing the cracked surface mechanically while the epoxy achieves initial set. Using the hull fitting bracket as a brace for his arm so he can maintain constant pressure for 5 minutes without his arm shaking. His thumb is against a cold, wet pipe that is leaking seawater at 45 pounds per square inch. His thumb is applying approximately 30 pounds per square inch of counter pressure. The leak rate under his thumb drops to near zero. The epoxy is curing. He holds. The forward equipment room is -2 degrees Celsius. At -2, a person holding a cold metal pipe in a static grip position loses dexterity in that hand within about 4 minutes. The hull technician's thumb begins to lose sensation at 3 minutes and 40 seconds. He does not move it. He is aware in the specific way that experienced tradespeople are aware of their tools, that his thumb is currently the most critical component in the ship's air defense system. A $2.2 billion warship, the Eastern Radar Arc, the Kola Peninsula, 280 miles away, still watching, and one thumb at -2 degrees, not moving. At 4 minutes and 50 seconds, he tests the edge of the epoxy with his fingernail. It has surface hardness, not full cure. Full cure will take 90 minutes. But initial set. He releases manual pressure. He waits 15 seconds. No flow. He releases fully. The crack is sealed. The water flow from the weld crack stops. The cooling line pressure holds. The SPY 1D Face Bravo receiver sensitivity, which has been degrading for the past 12 minutes as the cooling system operated with reduced flow through the crack area, begins recovering as the heat exchanger regains full supply pressure. The Combat Systems Officer in CIC watches the receiver sensitivity indicator on his display recover from 67% back toward baseline. At 2:24 a.m., it reaches 89%, within acceptable operational parameters. Face alpha remains offline. The phase shift deformation from the shock wave is not repairable at sea. It requires a yard calibration of the affected radiating elements, a process measured in weeks, not hours. The ship will operate with 3-face coverage for the remainder of this deployment. But 3 faces, including the recovered face Bravo, means coverage on the eastern arc. The ship can see to the east. The forward electrical panel has been inspected and found uncontaminated. The water that entered through the conduit seal pooled in the bottom of the panel housing and was removed with a bilge pump syringe before it could reach the bus bars. The panel is dried and returned to service. The conduit seal is temporarily patched until proper replacement can be installed. The drain mat blocking the floor drain is removed. Will not be used for that purpose again. The temperature outside remains minus 23 degrees Celsius. The icing crew goes out on rotation every 2 hours. The ship continues her patrol. The damage picture is specific. Face alpha offline for depot repair. Epoxy patch on the cooling line, a fix that the hull technician characterizes in his maintenance log as effective but unorthodox, requires yard follow-up. 7 external antennas with ice-related degradation, 3 requiring replacement. 2 CIWS barrel heating elements burned out from ice accumulation during the period when the heating system power was briefly interrupted by the electrical panel isolation. 1 additional item discovered during the post-event walkthrough at 0400. The cable run for the SPY 1D Face Alpha cooling water temperature sensor. A 24-gauge signal cable running from the forward equipment room up through a conduit to the CIC equipment rack has been partially severed by a fragment from the zircon's debris field that passed through the superstructure cladding above the bridge. The fragment itself was found embedded in the port bridge wing coaming. A piece of titanium alloy, approximately 4 centimeters by 2 centimeters, irregular, with one edge sharp enough to have cut the cable cleanly. The fragment weighs 23 grams. The zircon that produced it weighed approximately 3,000 kilograms at launch. The fragment is kept. It sits on the captain's desk in a clear evidence bag for the remainder of the transit. It is a physical record of the margin. 34 meters of vertical clearance, translated into 23 grams of titanium alloy that came through the superstructure cladding and cut a cable instead of continuing downward into the space where 3 crew members were standing. 1 zircon hypersonic system passed 34 meters above the flight deck at Mach 6. 1 SPY-1D array face taken offline by shockwave deformation. 1 cooling line crack from transmitted structural load, developing over 4 minutes and 11 seconds from hairline to active seep. 1 forward electrical panel threatened by water ingress through a blocked conduit seal. 14 minutes from leak detection to sealed repair. 1 wet surface epoxy application under manual pressure at minus 2 degrees Celsius by a hull technician who held counter pressure with his thumb for 4 minutes and 50 seconds in an Arctic equipment room. Eastern Arc radar coverage restored at 2:24 a.m. 1 23-gram titanium fragment recovered from the bridge wing coaming. Ship status, operational. 3 days later, in the debrief conducted at Tromsø, the senior officer reviewing the engagement noted that the epoxy repair was not in any damage control manual for pressurized cooling systems. He asked the hull technician where he learned the technique. The hull technician said he learned it from another hull technician on a previous ship, who had learned it from someone else. It had never been formally written down. It existed in the accumulated knowledge of people who work on ships, passed from hand to hand, watch section to watch section, deployment to deployment. The officer asked if it should be formally documented. The hull technician said he thought it probably should. The documentation was drafted. It was submitted for review. As of the date the ship returned to home port, the review process had not yet been completed. The knowledge remained where it had always been, in the hands that needed it.